And oh, uh, sorry, I should have waited for you to start recording. Okay, about these lectures, they're intended to be introductory or elementary. I am aiming for a graduate level, and they're intended to introduce the ideas of light front coordinates and kinematics and light front dynamics, light front quantization to an audience who might not already be familiar with it. Uh, so I apologize in advance to anyone in this audience who is a bit bored from this being too elementary. I saw some people on the participants list who are kind of light front veterans or even people who are responsible for light front physics being what it is today. Uh, and for anyone who needs more information, if anything I say isn't clear enough, if I don't give enough explanation, please feel free to interject with questions or requests for clarification. Uh, since I'm designing these as lectures rather than a seminar, I won't have citations on most of the slides. I dedicated slide space to try to be explanatory. Um, However, for those who are interested in digging deeper, here's a short list of some of the standard references on light front physics. Uh, there are, of course, many other sources that are really important besides these. This is not a complete or comprehensive list, so I also apologize to anyone I left out. But this is a lecture series. I'm going to be talking about a lot of physics that has been built up by many researchers. An outline for what I want to cover. I'm going to start with a very basic overview defining what light front coordinates even are and explaining some of their basic properties before going on to a conceptualization to try to give some intuition as to what this stuff means. Uh, then I'm going to talk about various aspects of kinematics. Uh, Boosts, there's something called the Galilei subgroup, which is kind of a personal topic of interest for me. Separation of variables and light front densities before moving on to dynamics. Things like light front quantization, Fock space, what a light front wave function is, before finally getting into a big example of how all of this is really important. I'm going to talk about parton distributions and deep inelastic scattering. Uh, Today, I'll try to get up to the Galilei subgroup, but I guess we'll see. We'll have to see how fast this all goes. So, going to start with the basic overview. So, light front coordinates are basically a reparameterization of spacetime. You take your standard Minkowski coordinates, which are also known as instant form coordinates, t, x, y, and z, and you define a change of variables. You define what are called x plus and x minus in terms of t plus z and t minus z. And then you keep the other two coordinates, x and y, the same, and you call these a transverse plane. Sometimes you collectively see these two coordinates referred to as x perp. So perpendicular to the longitudinal direction, which is along the z-axis. There are various conventions for defining light front coordinates. Some people say for x plus just use t plus z, some use t plus z divided by 2, and some use t plus z divided by the square root of 2. So in green, this 1 over the square root of 2 is a conventional factor that differs between some different authors. There are some very nice symmetry properties that you get if you use this 1 over the square root of 2, which I will touch on briefly. But throughout these lectures, I'm going to use the 1 over the square root of 2 convention. Now, x plus and x minus, there's kind of a symmetry between them in the sense that they are both what are called null coordinates. They are both coordinates along a light cone, but by convention, x plus is typically chosen by fiat to be a time variable. Uh, then, because time is in the x plus direction, fixed time surfaces are in the x minus direction. So if you look along this x minus coordinate, because your x plus is fixed, that's a fixed time surface. This is also the trajectory through space-time of a light front moving in the minus z direction. So your fixed time surfaces are given by light fronts moving in the minus z direction. If you personally are looking in the plus z direction, everything that a fixed light front goes through is considered to be fixed light front time. So, because we have these peculiar coordinates, there also are some peculiar things with index placement. But first of all, it's very helpful to have formulas not just for converting from Minkowski or instant form coordinates to light front coordinates, but going back. So your x plus is x0 plus x3 or t plus z, x minus x0 minus x3, with by convention this 1 over the square root of 2. One of the nice things about this 1 over the square root of 2 convention is that the inversion formulas to get x0 in terms of x plus and x minus, x3 as well, is that you have this 1 over the square root of 2 as well. So the symmetric inversion formulas are part of why this convention's nice. You would have to have different looking formulas for any other convention. So very easily convert between light front and instant form using a matrix. With the square root of 2 convention, the matrix and its inverse are the same. So basically, if you have a column matrix with your Minkowski coordinates or instant form coordinates, you can multiply by that matrix and this C matrix, and you'll get a column matrix in terms of light front coordinates. And because this matrix is its own inverse, you can multiply a column matrix in terms of light front coordinates to get something in terms of instant form coordinates as well. Similarly, if you have a matrix of some sort that acts on four vectors, I'll give a couple of examples of this briefly. Typically, when you do a coordinate transformation, uh, you would have something like you'd multiply the matrix on the left and the right by C and C inverse, since C inverse is C. You just multiply any matrix on the left and the right to convert the matrix from instant form to light front. So for four products, typically in your standard instant form of Minkowski coordinates, you'll have x dot y, you multiply the zero components, the time-like components, and then you subtract off the three vector product between the space-like components. So x0, y0 minus x1, y1, same for 2, same for 3. If you substitute in for y3, x3, y0, x0, the light front coordinates, so you use the inversion formulas, and you work out the algebra step by step, you get some cancellations. The x plus times y plus in both of these pieces from the 0 and the 3 parts cancel out, whereas the x plus times y minus end up contributing constructively. So the four product in terms of light front coordinates is off diagonal in these new coordinates. You get something that's like x plus y minus plus x minus y plus, and then minus the standard dot product between the transverse components of both vectors. You can use this to define your metric in light front coordinates, since your metric is something that is supposed to give you the dot product when you contract it with your upper index form of the four vectors. I just noticed this typo. This should be y nu here. So your metric is off diagonal. You have your standard minuses for the x and y components, And for the plus and minus components, you have 0 in the diagonal and +1 in the off diagonal. And it happens as yeah, there's a raised hand.
Sorry for disturbing. So I have a question. So the matrix that you showed in the previous slide that transformed curly C, I guess, or Z it is. So is it does it satisfy this Lorentz transformation like transpose like lambda transpose eta lambda is eta, that kind of thing?
So this is not a Lorentz transformation because it does not leave the metric invariant. Lorentz
Okay.
transformations always leave the metric invariant.
Yes.
So you would have to, if this were a Lorentz transform, get 1 minus 1 minus 1
Yes.
1 along the diagonal. So this is in fact not a Lorentz transformation. It's a subset of general coordinate transformations on the other hand.
Okay. So does it has any other physical, if it is not a Lorentz transformation, any other physical problem? I mean, issues?
Uh, I guess it depends on what you mean by physical issues. In the next subsection, I will go a bit into conceptualization of these coordinates, but you can't get to light front coordinates from Minkowski coordinates by a Lorentz boost.
Okay, thank you.
You're welcome. So yeah, as I alluded to in the previous slide, use this C matrix to convert matrices. And this matrix, of course, is not a Lorentz transformation because it does change the metric. But now I'll show that another way to get the metric in light front coordinates is with the C matrix. Yes.
I just want to make a quick comment for the previous question. The transformation x0 goes to x0 plus x3 is a translation, not a rotation. And since x3 depends on the coordinates, it's a general coordinate transformation,
Yes, it is.
namely a local translation.
Yes, it is. That's correct.
Okay, that was just a comment.
Thank you for the comment. That is a helpful clarification to make.
Yeah, but still it is not a Poincare transformation. That's what I was going on.
It is not a Poincare transformation
Yeah.
because it does not leave the metric invariant.
Invariant, yes. Thank you. Yeah.
Mhm. So you can actually work this out by doing matrix multiplication. Multiply your standard Minkowski metric, the diagonal one, on the left and right by the C matrix. And if you work it out step by step, you get exactly the same metric that you would infer from the 4 product. So this is a nice example of how useful the C matrix here is for converting between light front and instant form coordinates. This slide is just kind of a neat curiosity. If you look at events that are strictly in the TZ plane in Minkowski or instant form coordinates, or the x plus x minus plane in light front coordinates, the proper time is actually proportional to the area of a rectangle with the 2 events as corners and with edges along the light cone. And in fact, it's the square of the proper time is given by twice the area of this enclosed rectangle. Rectable there is a typo. Sorry about that. I don't know of any practical application for it, but I find that kind of a neat curiosity, so I thought I would point this out. Now, one of the peculiar things about light front coordinates, because the metric is off diagonal, is that you have some funny things happening when you raise and lower indices. So in any coordinate system, the standard thing you do when you raise or lower indices is you use the metric to do it. So if you have a contravariant or upper index 4 vector, you lower the index by using the metric. And if you have a covariant or lower index 4 vector, you use the inverse of the metric to raise it. One of the perks of the 1 over square root of 2 convention for defining light front coordinates is that the metric and its inverse are identical. If you used 1/2 or just 1 instead, then you'd have some factors of 2 or 1/2 in the metric that would be different between it and its inverse. So the square root of 2 convention just keeps everything a lot cleaner and neater. So because of this off-diagonal nature, raising and lowering indices swaps plus and minus. So x with a lower plus is equal to x with an upper minus, and vice versa. X with a lower minus is equal to x with an upper plus. So verbally, when we say x plus out loud, because x with an upper plus and x with a lower plus are different, when we say x plus out loud, we mean x with an upper plus, which is the same as x with a lower minus. And if someone says x minus out loud, they mean x with an upper minus. So we kind of prioritize the contravariant upper index form when referring to components verbally. Regarding derivatives, derivatives are primitively defined as kind of lower index things. Partial with a lower plus means the derivative with respect to x plus being x with an upper plus. So you can define the derivatives via the chain rule. Derivative with respect to x plus, you have something that depends on x0 and x3, and you want to take the derivatives of x0 and x3 with respect to x plus, which by the inversion formulas, each one of these is the square root of 2. So derivative with respect to x plus is the same as the sum of the derivatives with respect to x0 or t and x3 or z times 1 over the square root of 2. And similarly for x minus, you end up with derivative with respect to x0 minus derivative with respect to x3. So you can kind of summarize these as x plus partial plus or minus with a lower index is 1 over square root of 2 times partial 0 plus or minus partial 3. This also has implications for how we define the momenta. The four momenta are space-time translation generators and are thus related to these derivatives. So P lower mu is in general equal to I times partial lower mu. So that means that your time translation generator, since by fiat we decide that x plus is time, is equal to P lower minus, or the derivative with respect to x plus times I. So since that's your time translation generator, that's your Hamiltonian or your energy. And because raising and lowering indices swaps plus and minus, that means P upper minus, usually called P minus, is your Hamiltonian, and P plus, P upper plus, is a momentum component. As for if you have an on-shell particle, your relativistic mass shell condition should still be obeyed. So m squared is equal to the forward product of your momentum with itself. In terms of light front coordinates, that means you get twice p plus times p minus, so that's a momentum times an energy, minus p perp squared. You can invert this to solve for energy or the Hamiltonian, which is P minus, since that generates time translations. And you get this really nice looking formula, m squared plus p perp squared divided by 2 times p plus. This is kind of reminiscent of the non-relativistic formula for energy, where non-relativistically you have some constant, which in principle could be arbitrary or could be equal to mc squared from a non-relativistic reduction, but you have some constant plus p squared over 2m. So in this context, you have an energy formula in which p plus seems to behave kind of like a mass, and p perp kind of like a momentum. So that looks like a peculiar curiosity so far, but we are shortly going to see more examples of things that look kind of like non-relativistic, but p plus behaving kind of like a mass. Actually, we'll see one of these right away. You can define velocities or obtain velocities using Hamilton's equations. Basically, you take derivatives of your Hamiltonian with respect to components of the momentum to get your velocities. To be sure, velocity in this context means a rate of motion with respect to x plus, since we're working with light front coordinates, and by fiat, we've decided x plus is time. So your velocity of something in the transverse direction when you're measuring velocities as motion as x plus advances is equal to your perpendicular momentum, p perp, divided by p plus. And your v minus, your velocity in basically your derivative of x minus, your x minus coordinate of a moving particle with respect to x plus is going to be p minus divided by p plus. So basically your three components of your momentum are equal to p plus times your three components of your velocity. Kind of reminiscent of the non-relativistic formula P equals mv, with P plus behaving kind of like a mass. So the curiosity seems to run a little bit deeper. So the summary so far, we've defined light front coordinates and their conjugate momenta. X upper plus, which we call X plus because we prioritize the upper component contravariant forms when saying things verbally, is our time. So T plus Z over square root of 2. And P minus, which is your traditional energy, P0 minus P3 over square root of 2 is your energy. It's canonically conjugate to X plus. It generates your time translations. Your invariant four product and proper time are given by off-diagonal formulas. You multiply plus and minus components by each other instead of squaring them. And your P plus seems to act somewhat like a non-relativistic mass in your energy and momentum formulas. So this is, I think, a good point to break for if there are any more questions before I move on. Yes.
Thank you for the nice summary. Could you give some comments on the case of zero mass particles?
Yeah, zero mass particles. In the case of zero mass particles, you would just set m to 0 in these formulas. So the energy would be p perp squared divided by 2p plus. The velocity formula would still be the same. And of course, as usual, your zero mass particles would have trajectories moving along a light cone. So the formalism works just as well for zero mass particles. Was there a more specific question you had, though?
Maybe later, but thank you.
Maybe I have a follow-on.
There's another question online. Philip?
Yes. Adam, hello. I had a very quick two comments. Comment number one, the value of the 1 over the root 2 is that the Jacobian in going from x0, x3 to x plus x minus is 1.
Yes, that's correct.
And that means that dx0, dx3 is equal to dx plus dx minus. And that's a very valuable simplification.
Yes, that's a good point, too.
Yes, and the second comment is it's not, you don't take x plus to be the time by convention alone. What I was once able to show was that if you look at time-like events, which are the ones you get in scattering, then the sign of the x0 and the sign of the x plus are the same. But for time-like events, the sign of x0 is Lorentz invariant. Therefore, for time-like events, the sign of x plus is also Lorentz invariant, and therefore it should be the light front time.
Well, what I meant by it being by fiat is that we choose x plus rather than x minus to be time usually.
Well, no, I'm saying you don't have any choice. I'm saying is that only x plus is invariant for time-like events. Just like x0 is, x3 is not invariant for time-like events, but x0 is. And that's why x plus has to be the time in the light front case.
You're saying x minus, the sign of it isn't invariant for time-like events?
Yes, that's correct. Because
That-
the sign of x minus, I don't think is invariant, but the sign of, I mean, upper x minus, but the sign of x plus is definitely invariant. And it has the same sign. And the important point is the sign of x plus is not just invariant, but it has the same sign as the sign of x0.
I don't know that could be the case though, because
I proved this. Okay.
rotate your Cartesian coordinate system and z becomes minus z. Like the direction that x3 is in is arbitrary before you do the transformation.
No, you have to look at the line element. You have to look at you see x0 squared minus x3 squared minus x1 squared minus x2 squared is positive. And that fixes the sign of x0 minus x3 and x0 plus x3 to be the same. That's the it comes from the line element, not from the transformation. It's knowing that x0 squared minus x3 squared minus x1 squared minus x2 squared is positive that you can get a constraint. Anyway, it's just meant to be a comment. It doesn't. I don't want to slow the discussion down.
But if the sign of x0 plus x3 and x0 minus x3 are the same, then
They're the same, yes, but that's correct.
then
They can both be positive or both be negative. But when you make x plus positive, it has the same sign as x0. The sign of x0 is a Lorentz invariant for time-like events, but not for space-like events. In other words, you can't prove anything without looking at time-like events, because for space-like events, none of these things are invariant.
I don't see how that would be the case for x plus but not x minus, though.
Okay, well, we'll discuss it. We can discuss it afterwards.
There was another question by Hemant.
Yeah, I have a question about this P apparent z plus. So how is it related to the mass?
I'm sorry, I didn't quite hear what you said.
Hello, can you hear me? Hello.
Can you repeat your question, please?
I'm asking about this P apparent z plus. How is it related to mass?
So the P plus is not the same thing as mass. I'm just saying that you have formulas that look very similar to non-relativistic formulas, with P plus appearing in the same place in these formulas that mass would appear in the non-relativistic analogs. P plus isn't the same thing as mass, but in some ways behaves kind of like how a non-relativistic mass would.
Okay, thank you.
We had a no? You're sure? Okay. If there are no more questions for this section, I'll move on to the next one. This is going to be less mathy. This is going to focus on conceptualization instead. So one thing I kind of want to get out of the way is that light front coordinates are not the same thing as the infinite momentum frame. It's kind of a common misconception that they are, that you get to light front coordinates by boosting to infinite momentum. But in reality, you can use light front coordinates by starting in any reference frame and then defining the coordinates. In fact, you can even boost between different reference frames within light front coordinates. So instead, I'll talk about conceptualizing light front coordinates in terms of using a different synchronization convention, basically what we mean by time or what we mean by spatially distant events being simultaneous. So synchronization in light front coordinates is to be contrasted with what is often called Einstein synchronization, which is the operational procedure that you would use to synchronize spatially distant clocks in order to set up standard instant form or Minkowski coordinates. In Einstein synchronization, if Alice and Bob are both at rest with respect to each other and are some distance apart, to make sure that their clocks are synchronized to what you would consider the same instant form time, Alice would send a signal to Bob. Bob would immediately reflect it back, and Alice would receive the signal. She could use how long it takes for the signal to bounce back to figure out how far away Bob is. She can send another signal telling Bob what her current time is and how far apart they are. And then they can use the convention that the one-way speed of light is c in order to synchronize their clocks, account for the time delay. So if Alice sends her signal at a time TA, receives it back at a time TB, then Bob sets his clock after they exchange all the necessary information to the average of TA and TB. So basically, Einstein synchronization is defined to be isotropic. The speed of light is the same in all directions. On the other hand, light front synchronization is not isotropic. You define hyperplanes with fixed t plus z or fixed x plus to be simultaneous. So if Bob is in the plus z direction from Alice, then Alice sends a signal to Bob asking him what time it is. Bob sends a signal back saying it's TB according to my clock. And Alice immediately sets her clock to say TB, basically by fiat defining light to travel instantaneously in the minus z direction. So basically, you take what you see when you're looking in the plus z direction as happening right now rather than happening sometime in the past. Now, this might sound kind of peculiar, but it's been noted since the early days of relativity. In fact, in Einstein's original 1905 paper, that you only actually require the round trip average speed of light to be invariant under boosts. It's entirely a convention or a definition, as pointed out by Einstein in his original paper, that the speed of light be c in each direction during a round trip. It's a very convenient definition because of the isotropy, but it's not necessary. Redefining the time coordinate in any way, whenever you do some sort of general coordinate transformation, means that you're changing this definition. And light front coordinates are an example of changing the convention for synchronizing clocks. There's a really nice popular science channel that actually talks about this. Recommend checking out by Veritasium, called Why No One Has Measured the Speed of Light. Unfortunately, it's a bit of a clickbaity title. He's implicitly meaning the one-way speed of light rather than the two-way speed of light. But despite the clickbaity title, it's actually an excellent and very informative video. So, regarding boost and simultaneity. So foliating spacetime, basically meaning you slice it up into fixed time hypersurfaces. If you divide it up into fixed x plus surfaces instead of fixed t surfaces, then this foliation is invariant under z direction boosts. So if you use your standard boost formulas in terms of Minkowski or instant form coordinates, here I have a plus because I'm considering an active boost rather than a passive boost. And you take the t plus z over the square root of 2 is x plus, t prime plus z prime over the square root of 2 is x prime plus. Then you find that a z direction boost scales x plus and x minus by different factors, but the coordinates don't mix up. So anything you consider to be fixed time is still fixed time. Anything you consider to be simultaneous is still simultaneous after you do a z direction boost. On the other hand, the time is either redshifted, so you get something that's like time dilation if you do a boost in the plus z direction, or blue shifted if you do a boost in the minus z direction. This is in contrast with instant form coordinates, which always give you time dilation when you do boosts. But there's actually a very good reason for this difference, having to do with light front describing what you actually see, which I'll elaborate on in the next few slides. However, it's also nice to note that if you use the rapidity variable instead of velocity, so eta is the cosh, gamma is the cosh of eta, beta gamma is the sinh of eta, then you get these really nice scaling formulas for x plus and x minus. Basically, the exponent of eta or minus eta is what you scale them by for a z direction boost. Okay, so regarding time dilation versus these red shifts and blue shifts, to a certain extent, time dilation is kind of an artifact of using instant form coordinates. What do we actually mean when we say that you get time dilation when you boost a clock? It's really time dilation with respect to a reference frame rather than an observer. So say you have two people, Alice and Dora, who are at rest with respect to each other, and they're some distance apart along the z direction. They synchronize their clocks using Einstein's convention. The two of them together can constitute a reference frame. Now you have a moving observer, Bob, who carries some sort of clock. He moves from Alice to Dora at some fixed velocity in the z direction, v. Sometime delta tb passes on Bob's clock. At the start, Alice's clock reads TA, and at the end, when Bob gets to Dora, Dora's clock reads TD. What time dilation means is that the time elapsed according to Bob's clock is less than the difference between Alice's clock when he's coincident with Alice and Dora's clock when he's coincident with Dora. It doesn't come from comparing what Bob sees on Alice's clock at two different times or what Bob sees at Dora's clocks at two different times. It has to do with comparing his clock to clocks that have been synchronized at two different spatial locations once he passes those spatial locations. So his clock is slow compared to a reference frame. And this depends on these two clocks that he compares to having been synchronized using Einstein's synchronization. On the other hand, if Bob compares to, or if Alice compares to Bob's clock only, we don't involve Dora at all, we don't build a reference frame, we just take what Alice sees on Bob's clock at two different times. She either sees his clock running slower if he's moving away because of relativistic redshift, or if Bob is moving towards Alice, she sees his clock moving faster instead of slower because of relativistic blue shift. The redshift and standard redshift and blue shift formula involves the square root of 1 plus beta over 1 minus beta. If beta is positive, that is Bob is moving away, you get a redshift. Beta is negative, Bob is moving towards, you get a blue shift. And one of the neat things about the light front boost formulas is that it automatically gives you red shift or blue shift instead of you needing to go through a few steps. You first calculate the time dilation, then you calculate the fact that there's a time delay. So light front prioritizes what we actually see rather than building a reference frame and reckoning things with respect to the reference frame. So it makes certain things easier to calculate, makes other things harder to calculate. But one of the neat conceptual things about light front is that it prioritizes describing what an observer looking in the plus z direction actually sees and describes everything in terms of that. Another interesting aspect of what an observer actually sees, as opposed to what you would reckon from your standard Lorentz transformation formulas, involves what is typically considered an optical illusion, a Terrell rotation. So, using the reckoning of instant form coordinates, if you take an object that is moving in a direction transverse to your line of sight and you boost it by a velocity beta, you get in instant form coordinates a Fitzgerald contraction. Your object now is thinner, not appears thinner, is thinner by the reckoning of the reference frame by some factor square root of 1 minus beta squared. However, an observer would not see it contracted. In addition to the contraction, you have to consider that the object has some finite extent in the longitudinal direction. And because light in instant form coordinates travels always at a speed c, it takes longer for the back of an object, for light from the back of an object to reach you than light from the front of an object. So because of this time delay, the object is kind of skewed or stretched out. And the back of an object, when you see it, appears a distance beta times L further behind than a front of an object. So you end up seeing the side that is on the back if now you define the front as the direction that the object is moving. So the object appears rotated rather than appearing contracted. And in fact, you can see that there's kind of a sine-cosine relationship between the factor of how it's dragged out and the Fitzgerald contraction factor. The squares of these factors add to 1, so it's kind of like you have a cosine theta L and a sine theta L. So objects appear rotated. Penrose and Terrell both independently discovered it. It's often called a Terrell rotation. And you would consider it an optical illusion in instant form coordinates. However, in the light front, you take this seriously. In instant form, you say contractions are real. In light front, you say the rotations are real. They're both equally valid viewpoints. They're both valid coordinate systems. But they're kind of like two sides of the same coin, two ways of looking at the same thing. Another really interesting thing, if you work out the algebra of an infinitesimal transverse boost, so you get basically things modified linear and say it's moving along the y direction because we're looking in the z direction. T is modified by something proportional to y modified by something proportional to t. These are just the linear leading order terms, order beta. If you do a rotation around the x-axis, then t is invariant. It's isotropic. Your y variable and your z variable are rotated into each other. So for an infinitesimal rotation, you get something proportional to y changing by minus z, z changing by plus y. Now, if you convert these into light front coordinates, your x plus is modified by something that's linear in y in both cases. Y is modified by something that's linear in both x plus and x minus. X minus is modified by something that's linear in y. Now, something that's really neat here is that if you take your angle of your rotation equal to minus beta, you perform both what you would normally consider a transverse boost and a rotation. You can cancel out the change in x plus. So if you perform a boost, which induces a Terrell rotation, and you perform a counter rotation, you rotate the object in the opposite direction as the Terrell rotation, then you'll get that your light front time is invariant, and your change in the Your transverse position is now something that is linear in time. So this looks kind of like a linear velocity formula. In fact, if you took a delta y1, delta y2, took the difference, this would cancel out. So your combined transformation leaves time invariant, and you have an object that's moving in the y direction with an apparent velocity square root of 2 times beta. This kind of suggests a new generator that's a combination of an ordinary transverse boost and a counter rotation to cancel out the Terrell rotation. We call this a light front transverse boost. We also have a 1 over square root of 2 here, which then makes your velocity beta instead of square root of 2 beta. And you get something similar for a light front transverse boost in the x direction. But because of the right-hand rule, it's an ordinary x direction boost plus a rotation around the y-axis instead of minus. So summary so far for this section. Light front coordinates, conceptually what they do is they describe space-time as we see it, at least in the plus z direction when we're looking in the plus z direction. So we consider very distant events, no matter how far away they are, to be in the present instead of the past. Longitudinal boosts then produce your observed red shifts and blue shifts instead of time dilation. And ordinary transverse boosts produce the observed Terrell rotations instead of Fitzgerald contractions. Now, although we have ordinary transverse boosts and they explain or produce something we would actually see, you can define, and it is standard to define, light front transverse boosts in terms of an ordinary transverse boost and a counter rotation that cancels out the Terrell rotation, which leaves both surfaces of light front time and transverse spatial structure invariant. This, I think, would be another good stopping point for questions, if there are any. Yes, Wayne.
I just had a comment, and with the 3 different kinds of boosts, one of the neat things about them is they form a subgroup.
Yeah.
Standard boosts.
So I am running very slow compared to what I was planning to do, but a couple sections from now, I do actually talk about that subgroup. It's one of the things that I find the most interesting about the light front, this Galilei subgroup, and it's something I am planning to build up to. It's absolutely one of the coolest things about light front, in my opinion. I think it's great.
Can I ask you a quick question?
Of course, of course.
So the time dilation in this instant coordinates, we always have the time dilation, irrespective of which direction the 2 observers are moving.
Yeah.
But how do we, like in, you said like in light front, we can have both time dilation and, so how does it, how physically we can understand that?
So physically, it's just in terms of red shift or blue shift. So I should probably actually try to explain this slide a bit more, or explain what I was trying to say a bit more. Maybe I was too quick with it or too vague with it. So to use instant form intuition, I would describe both of these figures in terms of instant form coordinates is that in a reference frame that Alice is at rest in, Bob's clock is slowed down regardless of whether he's moving away from her or towards her. However, when he's moving away from her, each time he sends a light signal towards Alice every time a second passes on his clock. Every time he sends a light signal moving away, he's further away than the last light signal he sent. So it takes longer for the light signal to reach her. So you have a combination of time dilation and the fact that it's taking longer between each light signal. When Bob is moving towards Alice, his clock is still dilated with respect to Alice's reference frame. However, because he's getting closer, there's less distance to travel for each signal, so his light signals are taking less time to reach Alice. And in fact, that kind of overwhelms the time dilation, and Alice receives the signals more frequently than once a second. So that's kind of how you would reconcile the two different pictures. Lightfront then takes the fact that when Bob is moving away, Alice gets the signals less often as defining what happened with Bob's clock. Whereas if he's moving towards her, she sees the signals arriving more quickly. She sees Bob's clock moving faster. So she defines Bob's clock as moving faster because that's what she actually sees. So
Okay,
the pictures are actually consistent with each other. You can analyze either of them in terms of the other coordinate system. It's just you make different priorities about what you are considering to be the underlying picture.
okay. So it's like basically this red shift or blue shift. This is the main point here.
Yes, exactly.
Okay, thank you.
So in principle, I'm only supposed to have until 11 a.m. So there are 5 minutes left. I don't think there's enough time to really start the next section. So I guess for the next 5 minutes, I'm open to more comments or questions. Yes.
So,
Adam. Yeah, thanks, Adam. That's uh, you had a total of 54 slides for today's lecture?
Yeah, either for today's lecture or maybe the last section I was thinking, maybe depending if this was a bit slow, would be next week's, but looks like I already have enough for next week as well.
Yeah, that's fine. That's fine. It's good to go at a slow pace. Yeah, so let me thank you for the very comprehensive and clear lecture.
Oh, thanks.
And there are some hands raised, some questions. So please go ahead, Sebastian.
Yeah, thank you for the wonderful lecture, Adam. Okay, follow up on my first question on massless particles. How do we describe massless particles in 1+1 dimension when we don't have this p perpendicular squared in the dispersive relation in the numerator?
That's a tough question. I have not actually thought about that, so I don't have a good answer for it.
Okay, no problem. Thanks.
I will be honest, I think mostly either in 4 or 5 dimensions. I have not dealt very much with 2 dimensions, and the one time I did it was with massive particles. Sorry, I don't have a helpful answer to you.
Philip, you had a question?
Adam, I just did a quick calculation about whether x plus or x minus being the time is a convention, and I agree with you. It's only a convention. The thing that I was interested in is why would either of them serve as the time? And what I was able to show, and we mentioned it, x0 squared minus x3 squared is x plus x minus.
Yes.
And in instant coordinates, you can go to x3 equals 0. And you have x0 squared is x plus x minus, which means that x plus and x minus have the same sign. But when x3 is 0, t is equal to x plus x minus, which is 2x plus or 2x minus. So either of them have the same sign as t when you look at time-like separated points. And therefore, either of them can indeed serve as what we ordinarily understand as the time, namely forward in t is forward in x plus, or you could have called it x minus.
I agree with you.
So,
And that was the comment. Yes.
On that and quick comment, like so for time-like events, we have like x0 square minus x3 square is greater than equal to 0. Sorry, is greater than 0. So it's basically factors out in x plus and x minus, and both of them are treated in the same footing. So I mean, one would naively expect that any of them can be treated as time.
Yeah, I would think so too. It just seems to be convention that x plus is typically treated as time.
Yep. And thank you for this very nice lecture.
Oh, thank you. Thank you.
Meijan, you have a question?
Hi, and thank you for the very nice lecture. So in the first part, you have a space-time diagram showing delta tau square. And you mentioned there's a factor of 2 in front of delta x plus, delta x minus. So I wonder if this factor of 2 is related to the conventional metric you choose. So you choose x plus minus equal to 1 over square root of 2 t plus minus d. So if you don't have this 1 over square root of 2, would you still have a factor of 2 here?
The factor of 2 there is convention dependent. I believe if you don't have 1 over the square root of 2, the 2 is not here.
Okay, I see. And so this delta tau square is the delta of tau square or the square of delta tau?
This is delta tau squared. So this is the change in proper time squared.
Okay, so you square first, then delta.
Oh, no, this is the square of the change in proper time between them.
Okay, I see. Okay, thank you.
Yeah.
There were a few comments or questions in the chat, I think.
Yes. Did you want to read them out to Adam? Or should I read them?
I can pop up. In the example of Bob and Alice, do we have time dilation in light front coordinates? So in light front coordinates, what you have is it depends on whether Bob is moving towards or away from Alice. So in this case, I'm looking at things from Alice's perspective. Bob's clock is dilated in light front coordinates if he's moving away, but it's quickened instead of dilated if he's moving towards. So the dilation or the quickening is just given by the standard redshift or blue shift formula, because light front is basically just taking what Alice sees literally. We also have a comment from James Very. In 1 plus 1 scalar phi to the 4 light front field theory, the Hamiltonian has no kinetic term. Huh, that's pretty interesting. Thanks for pointing this out.
Yeah, can I ask a quick question? Sorry, I can't find how to raise hand actually.
It's okay, it's okay. You can ask.
Yeah. So what about the volume element in 3-dimensional or in 4-dimensional light cone systems? Like
So
3-dimensional volume element, 4-dimensional volume element.
So as Philip pointed out, for the 4 volume element, the Jacobian with the 1 over square root of 2 convention is 1. So the 4 volume element would actually just be the same, except instead of being dt, dz, dx, dy, it would be dx plus, dx minus, dx, d2 x perp. For the volume, for the 3-dimensional volume element, so just over space,
Yeah.
that's a bit trickier. So I don't think people usually deal with that because x minus as a spatial coordinate is pretty peculiar. I mean, it's also a null coordinate. It's also along the light front. There are like three momentum elements when people do things in momentum space and they're doing Feynman diagrams and integrating. But I don't think I've actually. Yeah, I am not sure what factors would appear there. There would be possibly some factor, I'm not sure, but it'd be like d squared x per d. Philip
I have
might.
seen that, in some of the notes, like they mentioned that the Jacobian for 3D is half then x plus then x minus. But I'm not sure how like that Jacobian can be constructed for 3D especially.
For a 3D volume element, I'm not sure off the top of my head. Philip, did you have something to say about this?
Yes. The basic answer is you take the metric and you take its determinant, and that gives you the Jacobian in any dimension, and all of these square roots of two factors all get taken care of by the determinant. Now, what's going on is you don't preserve the metric, but you preserve the line element, dx nu, g mu nu. That one is preserved by any general coordinate transformation, and the volume element is d4x times g to the half. And that is also invariant under a general coordinate transformation. But because we always work with Minkowski coordinates, we never see these extra factors which relate to the metric. But once you make any transformation out of Minkowski, even if it's just linear, like x plus is x0 plus x3, you've gone into a general coordinate system and you have to introduce a metric. And what Adam is doing is he's saying, look, life is easiest if you put in that 1 over root 2, because then all of these metric factors disappear. But to understand what's going on, you need to carry them. And so always don't look at the metric, look at the line element. And that's the thing that's preserved. And if I just make a comment, one of the reasons why, Adam will get to it, why is it instant time quantization and light front time quantization? Why did they describe the same physics? Maybe they're different physical theories. Well, the answer is because they're related by a general coordinate transformation. And as long as you have general coordinate invariance, which is what we believe is the case, then those two systems must be the same system. And physics in one frame and physics in the other must coincide. And of course, the whole point of what Adam and everybody else has been doing is these calculations become so much simpler in light front. And that's the magic. It's not that the frame is magic, it's that the calculations that you then do are so much simpler. Anyway, that was the comment.
Thank you for the comment.
Thank you for the explanations.
There's another question online. Why do we want to cancel this terreal rotation while constructing a generator in light front? We don't do it in the instant form.
So the reason that canceling it is nice is that, first of all, it leaves x plus invariant. So actually, this is something that I wanted to get to in the next subsection, so I'll elaborate on next week. But because you can construct this boost that leaves x plus invariant, and because your boost in the z direction, although it causes blue shifting and red shifting, leaves the foliation invariant, you now have a way with these to boost a particle from rest to any momentum while leaving your foliation of space-time into fixed-time surfaces invariant. Another reason that canceling out the terreal rotation is nice is because the transverse spatial structure is invariant when you combine the ordinary boost with the terreal counter rotation.
Thanks, Adam. There's a question from Hemant.
I have a followed-up question regarding that momenta space. So volume element, sorry. So in that, if we have a spatial volume element, then we have divided by two, and then the time derivative and the space derivatives. But if we take the momentum space volume element, then we divided it by the momentum. Then why is that? In some
So,
literatures, I have seen that.
so for the momentum volume element, so you have a D4P, which is going to be invariant because of these factors of the square root of 2, the Jacobian is 1. And if you have a mass shell condition, that's basically enforced by you basically have a delta function of m squared minus p dot p. So basically you have this is something where a virtual whiteboard actually would be kind of helpful, but you have a delta function that you can use to set p minus to the on-shell momentum. But because p minus is multiplied by 2p plus inside of the delta function, if you pull it out of the delta function, you get a 1 over 2p plus, which then appears in your 3 momentum element. So you'll get like a dp plus d squared p perp divided by 2p plus. It's basically the same reason that in instant form coordinates you'll have d3p divided by 2 times the energy.
Thank you.
Philip, you have a question?
Yeah, there's a comment by Sebastian. I wanted to make a response to it, but I don't know. I think Adam should address it first, I think, because it's directed to the speaker.
I actually do not know the answer to it, but if you have a helpful comment, I would appreciate that.
Okay, well, I'll make a comment on chiral symmetry breaking. What happens in instant time is the axial charge annihilates the normal vacuum, but not the spontaneously broken vacuum. Now, in light front, the same statement is true, but there's a difference. The axial charge annihilates the normal vacuum even if the fermion is massive. And that's why a lot of people have come to the conclusion you don't need spontaneous breakdown to generate a fermion mass. But that mass is still a mechanical mass. So you have an anomaly in one respect. The axial charge annihilates the normal vacuum even if the fermion is massive. But that's not spontaneous breakdown. You still have to construct the spontaneously broken vacuum. And when the axial charge annihilates that vacuum, then you get a Goldstone boson. Now, of course, in 1 plus 1, which is the question was raised to 1 plus 1 rather than 3 plus 1, in 1 plus 1, that's irrelevant because there are no Goldstone bosons in 1 plus 1 dimension. But in general, in 3 plus 1, if you want to get a Goldstone pion, you still need to have a spontaneously broken vacuum, even in light front, even though you can put a mass term in and have the axial charge still annihilate the normal vacuum. It's when the axial charge does not annihilate the vacuum that you get dynamical symmetry breaking. Okay.
Interesting. Thank you.
Sorry, can I follow up? Because the answer is very interesting. So when you say spontaneously broken vacuum, you, I suppose, imagine that we are talking about interacting field theory. Is that correct?
Oh yes. You can just think, you want to talk about the fermion mass, you need the expectation value of psi bar psi to be non-zero, and it's only going to be non-zero because of interaction dynamics. Namely, it's done by loop diagrams.
You mean when we consider fermions with non-zero bare mass or zero bare mass?
Zero bare mass, yes.
Okay, so what if we consider fermions with non-zero bare mass
Okay.
free theory of fermions on the light front.
Yes, that still is, even if you want to do that, you've still got to have, for spontaneous breakdown, you must have the axial charge not annihilate the vacuum. And you need a vacuum that the axial charge does not annihilate, and then you calculate the expectation value of psi bar psi in that vacuum. Another way to say it is you've made a Bogoliubov transform, mixing the Cartesian annihilation operators in going from the normal vacuum to the broken vacuum. So
Sure.
even if you were able to introduce a kinematic mass, that's not the mass that you're going to get by broken symmetry. Another way of saying it is this: if I go back to 4 dimensions, you still need to get a Goldstone boson. And what makes the Goldstone boson important is not that it's massless, but that in scattering processes, you get what's called an Adler zero. Namely, there are low energy theorems associated with Goldstone boson scattering that you don't get in the normal vacuum. And that, in fact, one of the reasons that people realize this is if you look at pi scattering, pi proton scattering, and compare it with proton scattering, pi proton scattering is suppressed because there's a low energy theorem that's active with the pion that you don't have in the proton, and that's what led to PCAC. Now, PCAC, of course, was always formulated in instant, and the transformation to light front is very similar. In fact, there's a big review that Stanley, myself, and Peter Loudon wrote, and we discussed the Ward identities in light front, and they're identical to the Ward identities in standard, but therefore when you take the matrix elements in the normal vacuum, you get an unbroken symmetry. In the broken vacuum, you get the spontaneous breakdown. And why everything carries over is because the Ward identities don't change their functional form. That's what we were able to prove.
Mm.
Now, the bad news is, if you think about it as bad news, in the front form, the Ward identity involves what are called the bad fermions. Namely, the fermions in light front are eigenstates of a projector operator, and some of them are eigenstates in a way that makes them non-local, and those are important in the broken symmetry Ward identity in light front coordinates. But they still give you the same Goldstone boson, the same Goldstone boson structure in the end. It's just that you have to be mindful of what are called the bad fermions. That was the surprise, and what the three of us showed was that even with the bad fermions, the Ward identities don't change in structure. Now I see that Yang Li has put his hand up, and he's even more expert on this than I, and so I expect he's going to make some kind of a comment.
So just to summarize, very simple summary. So if I take a theory of 3 fermions, massive fermions, let's say on 1+1 dimensions, does this theory has a chiral symmetry or not?
In 1+1, yes. Oh, yes.
Okay, even though the fermions are massive.
Oh, I'm sorry. I thought you asked me if they were massless. If they're massive, no, I don't think so. However, what we did agree is that Q5 still annihilates the vacuum even with the massive fermion. But I don't think that there's a chiral symmetry, if that's what you're asking. M psi bar psi is not chiral symmetric.
Okay, thank you.
So there's a question online I would like to answer. Is this particular combination of K and J, does it lead to a kinematical generator? And the answer to that is no. So the kinematical generators have to commute with the Hamiltonian, which these particular combinations don't. It's actually with the opposite signs that they commute with the Hamiltonian. These, on the other hand, commute with P plus, and they're related to the Galilei subgroup, which I will hopefully get to next time.
Thanks, Adam. There's a question by Yang.
Hi, Adam. Thank you for this very nice lecture. I actually don't have further comments to add. I agree everything what Philip Mahan said. I actually have another question for you. This is a question that you are probably going to talk about in future lectures. If not, I really want to get your comments or opinions on this one. So are you going to talk about the initial value problem in lifelong coordinates? Because there are some speculations and also some past investigations that even initial value problems on lifelong may not be well posed to some cases, especially when there are massless particles involved.
I wasn't planning to talk about it, and unfortunately, it's not something that I know very much about. I have heard about it being an issue, but I don't really know enough to say anything intelligent about it, and I'd rather not risk saying something stupid about it.
Okay, great. Thank you.
Okay, are there any other questions? Yes, Protic.
Not a question. It's like, would this material be available so that we can, do this calculation in our time? This slides and videos.
Sorry, could you repeat the question? I didn't quite catch it.
Yes.
So would you make these slides available? Yeah, that's what I'm asking.
Yes, the slides and videos will be
However, not actually finished yet, so probably I won't make them available until around the time of the third lecture. I've only finished the slides up through basically up through section 4. Although considering the rate I'm going at, I probably won't get through all 10 within 3 lectures anyway.
No, I'm not asking about the full. I mean, whatever you have covered, so that I can calculate the things that you have shown, like these things, in my spare time.
Okay.
The lectures, let me just add, the lecture is being recorded. The recording will be available. So even if you don't have the slides, you can go through the video.
Yeah, that would be nice. Yeah, thank you.
Okay. Adam, you better give us the good news or the bad news. Is the 54 pages the entire 10, or just what you plan to talk about this morning?
It's up to section 4.
Oh, okay. All right.
I guess that's the bad news then.
Bad news. We really have to find a way to enable these things to go much quicker. There's one simple solution. Don't let me say anything.
No, your comments are very valuable. Wouldn't want to make that restriction.
Thank you.
Okay, I don't see any other hands raised or questions in the chat. So let me thank Adam once again for the very clear and stimulating first lecture, and I look forward to the second lecture next Monday. And,
thank you.
In the meantime, I will send the link to the recorded lecture later today. Thank you, everybody, for joining.
Thanks.